So let's take a look at how we can use L'Hopital's rule to evaluate limits as we approach a particular number. This could be a number like 0 or 1 or pi, or something as we approach infinity or negative infinity. But typically what you're going to have is a little quote-unquote mini function over another. And this is going to be able to work in two different cases. Case number 1 is when you get 0 over 0, and case number 2 is when you get some version of plus or minus infinity over another version of plus or minus infinity. So let's work through some examples and we'll show you kind of how this works. The first thing, anytime I want to evaluate a limit, is I'm going to try direct substitution. When I put infinity in here into this function on top and bottom, numerator and denominator, I get infinity over infinity. Now, I know the result of this limit. I know that this thing is going to be equal to 3/5. I know that based on my rules of how this is going to act as we get infinitely large values of x, and I know that I can, when I have the same order in numerator and denominator, I can just compare coefficients. But let's pretend we forgot that rule for a moment and we wanted to use L'Hopital's rule. Because when I put infinity into the numerator and denominator, I got a version of infinity over infinity called an indeterminate form, right? This is my indeterminate form, infinity over infinity. I can use L'Hopital's rule. And you want to be careful. You don't want to write that this is equal to infinity over infinity because it's not technically equal to that. Instead, we want to just sort of note that maybe in the margin that this is the indeterminate form that we're working with. So then we can take the derivative of the top over the derivative of the bottom. And instead of comparing the little quote unquote mini functions that we have here, we can use the derivatives of them. So this is going to literally be equal to the limit as x approaches infinity of the derivative of the numerator, which in this case is 3, over the derivative of the denominator, which is 5. Well, there's no x's anymore in here, so I directly substitute infinity. I end up with a result of 3/5. And L'Hopital's rule is going to work that way every time. As long as we get an indeterminate form of 0 over 0, or plus or minus infinity over plus or minus infinity, we're going to be able to take the derivative of the numerator over the derivative of the denominator. Be careful. Don't confuse this with quotient rule. This is not a substitution for quotient rule. This is something completely different. This is simply using derivatives to help us evaluate limits. Let's take a look at another example. When I put in 0 for sine x over x, I end up with an indeterminate form of 0 over 0. So I can apply L'Hopital's rule. The derivative of sine x is going to be cosine x. So I have the limit as x approaches 0 of cosine x over, well, the derivative of x is just 1. And now when I directly substitute 0 into cosine of x, I get cosine of 0, which I know is just 1. And if I think back, this particular function actually had a hole at x equals 0 and a hole that had an output value at y equals 1. So this kind of makes perfect sense to me if I think back to what this function might look like graphically. Let's try another example. Here I put in x as x approaches 3. I'm going to directly substitute 3, and I get a 0 over 0 once again as my indeterminate form, so I can move ahead with my derivative. I can either multiply this out, or maybe I want to use the product rule. We'll use the product rule here in the numerator real quick. So I have 1 d2 plus 2 d1 over the derivative of the denominator, which is just 1. Now when I put in 3, I end up with 0 times 1 plus, if I put 3 in here, 5 times 1, or 5. Which is a really cool result because if I go back to this particular function, I know that I had a giant 1 there. This is really the same thing. If I get rid of that hole, if I get rid of that giant 1, this function looks a lot like x plus 2. It just has a hole at x equals 3. So whether I used my traditional methodology from way back in chapter 1 to get the result of 5, or L'Hopital's rule to get a result of 5, both of them yielded the same result. Sometimes it's not that simple. Sometimes I don't have a method that's going to work this way. Take a look at this example where I'm going to take e, I'm going to put e in here for x. I would end up with e minus e over 1 minus the natural log of e, which ends up with 0 over 1 minus 1, which is 0 over 0. There's my indeterminate form. Notice again, I didn't write that this was equal to 0 over 0 because I don't want to put that in on the AP test. They're going to mark me off if I do that. But because I have this indeterminate form, I can apply L'Hopital's rule, and I have the limit as x approaches e of the derivative of the numerator, which is going to be 1 minus 0, so just 1, over the derivative of the denominator, 0 minus 1 over x. I'm going to rewrite this guy as the limit as x approaches e of 1 divided by negative 1 over x. I have 1 divided by negative 1 over x, which is the same thing as 1 times the reciprocal, negative x over 1. So I know that this is equal to the limit as x approaches e of just negative x. When I put this in here, I end up with negative e as a result from my L'Hopital's rule. And so you can see that there might have been a hole in this particular function or something going on here that really had an output value associated with it. But we weren't easily able to find that hole like we were able to in the previous example. So L'Hopital's rule really came in handy. Finally, I know the result of this limit. I know this is going to be 0. It's an infinity over infinity indeterminate form. I know the result because the order is bigger than the denominator, that this thing's going to go to 0. But I'm going to use L'Hopital's rule just to double check my work real quick and show you a unique result. So in this case, I get the limit as x approaches infinity of 6x over 15x squared. And now when I directly substitute infinity in here again, unlike the case up here where this just kind of worked out, I end up with another infinity over infinity. I end up with another indeterminate form for which I need L'Hopital's rule. So I'm just going to use it again. And I get the limit as x approaches infinity of 6 over 30x. And now when I directly substitute infinity in here, I know I'm going to get 6 over some really, really, really large number, which is going to send this thing all the way to 0. So even though I knew the result was 0, I was able to actually apply L'Hopital's rule 2 times in order to get to my final result and kind of confirm that I was correct. So hopefully this comes in handy when you have some different and interesting cases as you continue your work through the calculus course.